Hello, we're going to talk today about carbocations. And so carbocations, and I'm going to draw one, say something like that, with a form positive charge. We know that is an electrophilic species. We have a form positive charge. Octet is incomplete as a carbon. Now, different carbocations, depending on the substitution here, will have different stability. And see, for example, if you had, and I'm going to draw now the carbocation, say, in the plane perpendicular to the screen right here. And I'm going to draw hydrogen, 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 and my empty p orbital like that. Now, that is what we call a metal carbocation. Now let's replace one of the hydrogens by, say, a metal group. So I'm going to keep drawing that. I'm going to do this. But now this one, well, still we have the empty p orbital. And now we have a carbon here, and we will have this in this metal groups, 3 bonds to hydrogen. But now I'm going to draw this bond to hydrogen explicitly. Now we can see that we have somehow a lateral partial overlap between the empty p orbital and the sigma bond here. And so by replacing one of the hydrogens, we're helping stabilize that positive charge. That is called hyperconjugation. And due to hyperconjugations, then a primary carbocation is more stable than a metal. So I'm going to say more stable like that. But what if I had a metal here? I would have more chances of doing this, say, lateral overlap. So secondary carbocations are even more stable than primary, and tertiary, meaning replacing each one of these by, say, carbons, and giving it more chances to do those overlap. So in general, we're going to say then that, let's draw, say, this, if we call this R, then this is tertiary. That's a tertiary carbocation is more stable than, say, a secondary. And here, you know, a secondary, notice that we have 2 R groups attached to the central carbon. Here you have 3. Yes? And now, lastly, we know that that's secondary, this picture here, we have 2 R groups, and that's more stable than a primary. And here I have hydrogen, hydrogen. So again, we see here that we have only 1 R group. So more stable the tertiary, more stable tertiary than secondary. We see 2. Here we have 3 R groups. Here we have 2. Here we have 1. In that more stable than the metal. Because of that, reactions that involve carbocation formation are faster when we have tertiary carbocations than if we have secondary. Now there is another, a couple of carbocations that we want to consider here in regards to the stability. And say that we have now this carbocation. This is allylic. So the allyl carbocation, we know that we can stabilize that by resonance. We can draw this resonance structure. And now this carbocation, by stabilization via resonance, is very reactive, despite of the fact that it's primary. Notice that here where the positive charge is, we have only 1 group. So it's very reactive. Another example that we want to keep in mind and consider is the benzyl carbocation. So now this structure, the benzylic carbocation, we can stabilize by resonance. Notice again, the positive charge, this is a primary carbocation, but because we can do resonance, Now the carbocation is stabilized. And now I'm creating a positive charge here, and I can continue doing resonance. So I'm going to move up. And in doing that movement, I am putting a positive here. And now I have another resonance structure. And yet I'm going to have another. So the benzylic carbocation is stabilized by resonance, and it reacts faster than it will do a normal primary. So benzylic carbocations are in general more reactive in allylic than even tertiary carbocations. And now the fact that we know how are they in regards to stabilization is important, because now we're going to study in another video carbocation rearrangement. And they happen when we have a carbocation that is not as stable. For example, secondary, it may rearrange to something better, to a tertiary, for example. But here, keep in mind that then we have seen that in general, primary carbocations are not stable. But if we have resonance, such as the case of the allylic carbocation or benzylic here, then those carbocations are more stable, and so they are reactive. They form, say, under conditions, for example, of SN1 reactions, which form carbocation intermediate, they are reactive. We're going to see more of that also later when we do problems of SN1 reactions.